So the volume of the gas is negligible compared to the volume of the space. So which one is the gas with the least intermolecular force? Is one that is non-polar and the least number of electrons, right? So I would say that X is nitrogen because it is composed of only 2 atoms and it's non-polar, and it has less number of electrons compared to carbon dioxide. Carbon dioxide is also non-polar, but it has more electrons, so stronger van der Waals. Okay, and the least ideal would be ammonia because it has hydrogen bonding, so IMF is not negligible. So C is the answer. Gas law can be summarized with this. The graph of PV over T against V is a horizontal line for a given mass. So PV over T, this T go down here, and for a fixed amount of number of mole of gas, and R is constant, so it is true that PV over T is a constant. Okay, PV over T equals NR, and these are constant, so PV over T is a constant. So it doesn't matter what it is plotted against, it will still be a constant number, right? Horizontal line. Next, the density of a given mass if an ideal gas at constant pressure is inversely proportional to the temperature. So it's saying that we know that density is gram per volume, right? Yeah, gram per volume. So it's actually equivalent to mole per volume. All right. So PV equals nRT. N over V equals P over RT. Okay, and this is equivalent to density. Constant pressure, so pressure is constant, R is constant, and yeah, so what we get is N over V equals 1 over T. So it is correct that to say that density is inversely proportional to the temperature because it's 1 over temperature. Okay. 3. The volume of a given mass of an ideal gas is doubled if the temperature is raised from 25 to 50 degrees Celsius. So guys, remember that so this is telling us it's telling us this. For a fixed mole of gas, right, the volume of the gas will double when the temperature is raised from 25 to 50 degrees Celsius. So PV over T equals NR, which is a constant. All right. So it's saying that P1 V1 at this condition, okay, pressure, volume, and temperature of the first condition equals P2 V2 over T2, correct? Because the mole is the same. So P1 V1 T1 equals P2 V2 T2, which is equal to NR. All right. So if I double the temperature, all right, if I double the temperature, then the volume will also double. Wait, if I double the temperature, okay, this will also double. All right, at constant pressure. Oh, pressure is constant, so we don't even need this. All right. Why is it double? Is because you want to keep the value of nr a constant. So if you double the denominator, the numerator must double so that they can cancel each other, and then the nr is still the same, correct? But the thing is, temperature we always measure in Kelvin, not in degrees Celsius. So if I am changing the temperature from 200K to 400K, then only volume will double. But 25 to 50 degrees Celsius, that's not doubling the temperature. That's just raising the temperature by 25 degrees. All right, so 3 is not correct. Mm, 6, we want to assign the oxidation number. If you calculate this C is 0 and this C is +2 and this chromium is +6 +3. Now we balance the number of atoms that change oxidation number. So I need 2 chromium there. So I'm gonna multiply this by 2, this one also by 2, because I have 2 chromium. Carbon is already balanced. So then from 0 to +2, that's a loss of 2 electrons. And from 12 to 6, that's a gain of 6 electrons. So I'm going to multiply the 2 electron by 3. So this multiply by 3, that multiply by 3. And then we balance the O. I need 4 oxygen over here. And then we balance the hydrogen. So I need 8H plus over there. HCHO, right? H can be plus, can be minus, depending on what it binds to. If it binds to non-metal, hydrogen is always the least electronegative. The least electronegative will take the positive oxidation number, right? But if it binds with, let's say, metal and AH, right? Metal is always more electropositive than non-metal. So the metal will take positive oxidation number and hydrogen will take negative oxidation number. But if it binds to non-metal, the hydrogen is the least electronegative of all non-metals. So it is the +1. O is very electronegative, so that is -2, and that's why C here is 0. Okay. 7. So PV equals nRT. Actually, you can use, oh no, this one is density. Oh my. And molar mass is mass over mole, right? So if we want to substitute this mole, okay, mole equals mass over mr. So we will put this in and substitute n. PV equals mass over mr RT. So mr equals mRT over PV. So you just plug all the numbers in. Remember to convert 27 degrees Celsius to Kelvin. So that would be 300. R is already correct. Mass is already correct. And then P is in the unit of Pascal. So these two are correct. And V, volume, is in the unit of m cubed. So you have to convert cm cubed to m cubed. That would be A. Okay. Which graph correctly describes fixed mass? That means n is constant. Yeah, okay. So so see A, PV equals nRT. Now, if n is constant, r always constant, and t is constant, that means PV must be constant. So, the graph should look like that. For B, n is constant, r is constant, t is constant. Wait, what am I? Oh, so P is equivalent to 1 over V, right? So the graph should look like that. If you don't know why the graph looks like that, you ask Mr. Charles. And then we have constant pressure and constant mole and constant R, and V is equivalent to T. So if V increase, T increase. So C is correct. PV equals nRT. N and R are constant. V is constant. So P is equivalent to T. So if P increase, T always also increase. Question? Are you thinking, oh, how come when Miss Lina is explaining it looks so easy, but when you're figuring out on your own, it's almost impossible? If you don't understand, you have to ask me. Okay. Next. So chromium only shows one time, right? Chromium is from +3 to +6. So that means the chromium is oxidized. So it is a reducing agent, but it's not an oxidizing agent. Hydrogen peroxide, O here is -1 oxidation state. Okay, O is always -2 except for peroxide ion. So in this case it's -1 and it becomes -2 here, -2 here, -2 here. So hydrogen peroxide then becomes water. All right. Yeah. So it is undergoing reduction. So H2O2 is an oxidizing agent. That is correct because it undergoes reduction. So B is correct. I minus is -1 here, and on the other side, I is +7, not -1, because the O is more electronegative than I, right? So O is the one that takes the negative sign, -2. As a result, I is the plus sign, okay? So I here is oxidized. So it is not an oxidizing agent. I minus is not. It undergoes oxidation. OH minus, OH minus is not changing, and there is no change in oxidation number from OH minus, -2, and this is still +1, and the hydrogen here in water is also +1. So OH minus is neither, okay? It doesn't undergo redox. Okay. 10. Liquid water and its vapor are at equilibrium. The equilibrium vapor pressure can be increased by increasing temperature, because increasing temperature means it shifts to the endothermic direction, which means liquid going to gas. This is increased, so it creates higher vapor pressure. Okay. Question 11. Most of you got this, but some of you did not begin from ideal gas equation. So you have to start from PV equals nRT. B, I think all of you got this. Yeah. So we just use this equation, plug it in. M equals 1120 times 8.31 times 298 divided by pressure in kilopascal, 101300. Okay, answer is 27.4, but please write down the unit, gram per mole. Calculate molar mass. Molar mass has a unit, right? Gram per mole. But MR, relative molecular mass, or AR, relative atomic mass, when it's relative, it means it's compared to something else. In this case, it's compared to the mass of 1/12 of the mass of carbon-12 atom, right? When you compare something, there is no unit. Like I can say, oh, my son is more handsome than so and so, right? There is no unit to compare the handsomeness. So that's relative molecular mass, relative atomic mass. They don't have a unit. But molar mass is the mass of 1 mole substance, so it's got a unit of gram per mole. In AS level, there are a lot of questions like this that assign you 1 mark for unit. State the physical condition under which, unless the unit is already given, so it will say molar mass equals ... and then gram per mole. Then the unit does not carry a mark because it's given, right? But if it's not given, it will carry a mark. Okay. C is good. D. D. All right. So, real gas has intermolecular force, right? If there is intermolecular force, then it will reduce the volume, because when gas particles are attracted to each other, they will be closer to each other, right? So it will reduce the volume and also reduce the pressure. Okay, so that's how intermolecular force skew this ideal gas equation. And also, real gas occupies volume. So it's saying that the volume of the gas particles is not negligible compared to the volume of the container. All right, and also when colliding, real gas when colliding, real gas lose kinetic energy because the energy is converted to other forms of energy. But ideal gas is assumed to have elastic collision, so there is no loss of kinetic energy, right? So you outline the three assumptions, rather the opposite of the assumptions of ideal gas. Okay, number 12 is very important. State the color change when this is converted to this. So all of these, all right, happening in a titration reaction. All right, so when you have your KMnO4 and Fe2 plus here, right? KMnO4 is purple. Now, when do you stop titrating? What is the end point? So the end point is purple turning pale pink. So this solution, you will only stop titrating when it turns pale pink. So this question is actually asking you the end point of the titration, which is purple to pale pink. If you stop when it is still colorless, then it hasn't reached the complete reaction yet. The reaction hasn't finished, right? There is still Fe2 plus that has not been oxidized. So this is actually asking you what is the end point, right? If you have Mn2 plus in solid state, okay, so it's undiluted, it's just pure, it's very, very highly concentrated, pure, all right, pure. This will be very, very pale pink. But the pink here is not because of the color of Mn2 plus itself, because it's already been diluted, right? So you can't really see this very, very pale pink. You can't see it. But this pale pink is the first few manganate ion that cannot be reduced, that don't get reduced because the iron 2 plus has been used up. Okay, so that is where this pale pink is from. I can say that this pale pink is from the small excess of manganate ion that you add that don't get reduced anymore because Fe2 plus is has run out. Okay, but when manganese 2 compound, a solid one, if you observe one, it's really very, very, very pale pink. When you dissolve it in water, it just looks colorless solution, right? That's how pale the pink is. It's very pale. Okay, so if you get this kind of question, if you have this kind of question, not in titration, okay? If you remember ethanol, and then you add a few drops of KMNO4, all right? This is purple. Now this is not titration, okay? So what you are observing is just what will these drops turn to, all right? Of course, you will see colorless. You will not see any purple here when you add the potassium manganate, because ethanol is still in excess and you're just adding maybe 5 to 6 drops. It's not enough to oxidize all the ethanol, so ethanol is still in excess. So in this case, the observation would be purple to colorless. But for titration is purple to pale pink. Okay, next. Twelve A2 so we have this volume and this concentration. So N equals the volume times concentration. Please maintain 3 decimal place. But here I did not deduct any points because the mark scheme doesn't have it. But just in case, please maintain 3 decimal places for good habit. And calculate the number of mole of MnO4. So it's 5:1 ratio. So the mole here is 2.5 times 10 power negative 3. Divide by 5. And it is 5 times 10 power negative 4 mole. And calculate the concentration. So concentration is MnO4 minus mole, which is 5.00 times 10 power negative 4, divide by the dm cube, right? So you go back here and you say, oh, it's 20 mil. So what dm cube is that? 0.02 and dm cube. So I'll give you 0.025 mole per dm cube. Now this, you are going to need it for the next calculation. Okay, so it's still continuing to here. Okay, so this one, oh yeah, so this one is 0.025 mole per dm cube of concentration, okay, from the previous calculation. During this titration, this one, NO2 minus become NO3 minus. Half equations will show electrons. Half equations always show electrons, okay? First, we balance the O using water and then balance the H using H plus, because here we have sulfuric acid, right? So it's in acidic condition, so we use H plus, 2 of them, all right? And then we balance the charge using electron. So here, total charge negative 1, total charge here positive 1. So I need 2 electrons to balance the charge. So oxidation number of N change from +3 to +5. Balance ionic equation between this and this. Okay, so we have The equation of manganate is MnO4 minus become Mn2 plus and 4 water, right, and 8 hydrogen, and then I need how many electrons here? Plus 2 plus 7, right? So 5 electrons. Now the balanced ionic equation will be these two, all right? Make sure the electrons are the same number so we can cancel. So here I'm going to multiply by 5. Here I'm going to multiply by, is it correct? Yes, by 2. And I will cancel whatever I can cancel. So for example, the hydrogen I can cancel, the water I can cancel at the end. Okay, I'm just going to do this first. 5NO2 minus 5 water, 16H plus 2MnO4 minus 5NO3 minus 10H plus 2Mn2 plus and 8 water. So I'm going to cancel this water and 3 here, and this H plus and 10 here. Yeah, that will be my answer. So I have to rewrite everything. All right, don't give me this. You have to rewrite everything after you cancel, then what you will get. Okay, wait, this one is 6. This one is 6. 6. You cancel 10H plus. All right, any question? No. Next, calculate the concentration of XnO2 used. So first you have to find the mole of KMnO4 because you know the concentration 0.025 times the volume 25 ml, right? 0.025, so that gives me 6.25 times power -4 mole, and then find the mole of XnO2 using the molar ratio. Molar ratio is 5 to 2. Okay, 5 to 2. So we have 6.25 times 10 power -4 divide by 2 times 5, and then concentration is just mole divided by dm cube. So the dm cube is here. The volume is here. Where is it? Here. The volume. Okay. So it should be 0.1 molar. Okay. Calculate the molar mass of this. So molar mass equals gram per mole. The gram is given in the question 14.7. The mole is calculated in here. Wait. See, this much XnO2 is dissolved in 1 liter of water, right? So in 1 liter, there is 14.7 gram of XnO2. And in 1 liter, there is 0.1 mole. So we know that 0.1 mole is actually 14.7 gram, right? So what's the molar mass? Is 14.7 divided by the mole. Okay, so that will give me 147 gram per mole. And 147 is the mass of X, mass of N, mass of two O's. So AR of X is 147 minus 14 minus 2 times 16. So that's 101. So if you go to the periodic table and find the mass number, not the atomic number, but the mass number, it's ruthenium. What effect would it have on the volume of XnO2 solution used in the titration if an old unstandardized solution of this were used? So remember, KMNO4 is actually not a stable compound, right? Because some of the manganese have been reduced to maybe +4 or +2 oxidation states, all right? And remember, when manganate ion, when it breaks down or decomposes into MnO2, all right? So this MnO2 has an oxidation state of +4 for the manganese. This will catalyze the further decomposition of manganate ion. So actually, the concentration of KMNO4, the actual concentration, is lower than it's supposed to be. That means that means, see, the burette is the one with this nitrite solution, right? So this is the nitrite solution, NO2 minus, and this is the one with KMNO4. So if the concentration here is lower than what it's supposed to be, then the volume of nitrite ion that is required is also lower. Okay. Now, in this reaction, and it says in the question, it says that sulfuric acid is added in excess. Okay, so if it's already in excess, it doesn't matter if you use more than what is used in this reaction. So no change, because it's used in excess anyway. Right? So if the acid is in excess, it doesn't matter if you use more than the original volume, or if you use burette, pipette, or measuring cylinder to measure. It doesn't matter. Okay, that is all for the unit test. Any question? No question. Okay. Wait, how many of us are here? Quite a lot. Thank you very much. Okay, I will just continue a little bit with equilibrium. Okay. So yesterday we already did a simple calculation. It's when we are given the mole at initial, right? And then we are given the mole of one of these species at equilibrium, and then we find out how much of the other species present in equilibrium. Okay. Now, to measure how much this equilibrium lies to the right or to the left, we use what's called as the equilibrium constant, or Kc, equilibrium constant, right? It's basically just telling us the ratio of the products of concentration of the multiplication of the concentration of products over concentration of reactants. Okay, so if there is a lot more product at equilibrium, if there is a lot more product, then the value of the numerator is big, and the value of the denominator is small. All right, because you cannot have a lot of product and a lot of reagent. You either have more product and less reagent, or more reagent than product. Okay, so if the numerator is a big number and denominator is small, then Kc value is big. So what does it mean? If Kc value is big, that means equilibrium lies far towards the right. Okay, but if we have if the equilibrium lies towards the left, that means there is more of this, denominator is bigger and numerator is smaller. So that means Kc will be small. So Kc small indicates that the equilibrium lies towards the left. It doesn't react that much. Okay, like in Haber process. In Haber process, only 15 to 20% yield. That means equilibrium lies more to the left rather than to the right. Okay. Now, how do we calculate Kc? So this is the formula: concentration of C, the product, to the power of its coefficient times, so this is times, not plus minus, is times the concentration of D to the power of its coefficient divided by concentration of A, which is the reagent, times to the power of the coefficient times concentration of B to the power of the coefficient. And then Kc unit will depend on the Kc expression, right? So this Kc is called equilibrium constant, and this whole thing is called the equilibrium law or equilibrium expression. Okay. Now, what if Kc is 1? right? We already say large Kc, that means equilibrium favors the right. Small Kc, equilibrium favors the left. Kc equals 1, that means the amount of reagent and products is more or less the same. Okay, so equilibrium is like almost right in the middle. Okay. Now, what if you change condition of the reagent of the reaction? Okay, for example, you change the concentration. Now, if you change concentration, let's say I want to increase the concentration of A. All right, I want to increase the concentration of A. So this concentration is going to increase, but by law, Kc should be constant. Kc is only dependent on temperature. Only temperature can change Kc. All right, concentration cannot change Kc. So if I increase concentration of A, how do I make Kc constant? Oh, I have to increase the concentration of C and D so that concentration of A will decrease. Do you understand? Because if you increase concentration of A, how do you make sure that Kc remains constant? You have to have higher concentration of C and D. And that is why if you increase concentration of the reagent, equilibrium shift to the right because it wants to increase the concentration of C and D so that the numerator, all right, will increase. Of course, the concentration of A will decrease a little bit to make C and D, right? So that Kc stays constant. All right, so the goal here is always to make sure that equilibrium constant stays constant. All right. Similarly, if we separate D, okay, eliminate D, then D will go down very drastically. This value will drastically go down. So then how do we make sure that Kc stay constant? We also have to reduce the denominator. So how do we reduce concentration of A and B? We need to shift the equilibrium that way so that B and A concentration will also decrease. That way, Kc will be preserved. Okay, so this has to do with what you know as Le Chatelier's principle, and we will review that like on the last few pages of this notes. Okay, so far, are you good? Is there any question? No? I'm sure you already have received your new timetable, so we will follow that from tomorrow. Okay? I will see you tomorrow. Bye-bye.
Thank you.
Thank you.
Miss Lena,
Yes.
I have a question.
Yeah.
Can you go back to the unit test paper?
Yeah.
Can you explain like the structured question 1D again? D dog.
This one?
Yeah.
Oh. It's just basically asking you why we cannot use this equation for real gases, right? So we say, or because real gases have intermolecular force.
Oh, okay.
Yeah, so if real gases have intermolecular force, so these are gas particles and they are attracting each other, right? So if they are attracting each other, they will come closer to each other, right?
Yeah.
So that will affect the pressure as well, because they will attract each other, so they do not like bounce or hit the wall as many times or as strongly as an ideal gas. An ideal gas, they are not attracted to each other, so they just bounce and bounce and just fly around very freely. But real gas, they have intermolecular force. Yeah. But basically, you are just saying that um, the the opposite of ideal gas assumption.
Okay. And can you go to the next page? Oh wait, not this page. The last page. Sorry.
Last page.
Yeah, I just want to see it again.
Right. Is it this one?
Uh, yeah.
Yeah. Which part?
Uh, the I wait. The whole page.
Whole page.
Thank you.
Wait, Miss Lena, what
Yeah.
do you mean by KMNO4 like decreases?
Oh, okay. I'll show you here. Do. Here. So this is from your notes, page 12, redox notes. Potassium manganate is not a stable compound. That's why it's not used as primary standard. And it's because it undergoes auto decomposition. So potassium manganate 7 will decompose to manganese 4 oxide, right, which is this one. And this manganese 4 oxide will catalyze the decomposition of more manganate ion. So it always has to be prepared fresh. First, it's prepared fresh, and also once it's prepared, we have to test it against a standard solution so that we know exactly what the concentration of manganate 7 solution is. So yeah, this is the decomposition, and then this is further decomposition. All right, so this is actually redox reaction. So Mn, this is reduction, and this one is the oxidation.
Miss Lena.
Yeah.
Do we have to know like in the structured question? Are they gonna ask um like a question where we have to answer like potassium manganate is not a primary standard and then explain like blah blah blah? Or like do we need to know like what auto decomposition is? I mean technically it's just decomposition, right?
Yes.
Okay.
It just means that by itself, just in water, by itself and water, it can decompose. So yeah, it doesn't need any other agent, like this only react with this to get what, or this needs to be heated to become what. No, it just decomposes by itself, just in water. Yeah, auto decomposition.
Wait, and also like in the decomposition from like potassium manganate to manganese oxide, there has to be like water
Yes.
in the reactant, and in the unit test, like the last question, it also has had a decomposition of like NO2 to NO3, right?
Oh,
Wait,
NO2 to NO3 is not decomposition.
no, I mean like you
It's
also still wrote water on the
oh
reactant side.
yes. So manganese, the manganate ion will still undergo decomposition with water very, very slowly. But the point for this reaction is that manganate ion oxidizes nitrite ion. So for this part, you are not taking into account that manganate 7 is also undergoing a secondary reaction, which is the auto decomposition. You're not mixing it with that. It is happening, but very, very, very slowly. But in this question, what is the main thing that's happening is the nitrite getting oxidized by manganate 7.
But for this like entire page, question A, like the first, like I,
Yeah.
I mean not, I mean
So
not A, like
this entire question, you have two titrations. The first titration, which is question A, is to standardize manganate 7, right? To standardize manganate 7, because we know manganate 7 is not a good primary or a standard solution because it's unstable, it undergoes auto decomposition, right? So that's why we have to check against iron 2 and see what concentration are we left with in the manganate 7 solution. So this part A of the question is just to calculate the concentration of manganate ion, right? And then we use that concentration to do the second reaction. The second reaction is manganate 7 reacting with nitrite ion, and nitrite become nitrate, and blah blah blah. Yeah.
wait, so the reason why in the question BI you wrote H2O is because NO2 was in
Oh,
deionized
I
water?
use H2O because I want to. This is just a balancing half equation. So I
Oh,
have
so you
two
just
O
added
here,
water.
3O here. So I need one more O. So I put
Oh,
in water.
okay.
Yeah, and then I put in H plus because I need two H pluses, two H's to balance the water. Yeah.
Okay, thank you.
hmm And why manganese 2 plus is pink? Why? Uh, okay, wait. I just want to show you if I can get. Oh, yes, I can get it. Mm, so, where do I go? Oh, stop presenting, and then here. These are examples of manganese in 2 plus oxidation state. It's pink. It's pale pink. But if you dissolve this in water, you hardly see the pinkness. So it's like, if it's dilute solution, it will be colorless. Yeah. But if you are answering questions about titration, so you need to know the context of the question. Is it titration or is it just testing for reducing agent, or testing or oxidizing ethanol or something like that? So if it's titration, you want to give me the color of the endpoint. So the manganate 7 is deep purple, right? Purple, and then the endpoint is pale pink. That's when you stop, right? That's the endpoint. The endpoint is the change of color when you stop titrating. That's the endpoint. So you stop at pale pink. But for titration, the pale pink that you see is not because of the color of the manganese 2, but it is because of the excess manganate 7. So if you have a very little bit of the purple color in a whole bunch of water, it actually looks pale pink, right? Yeah, so that is why you have to say purple to pale pink. But other practical that I have seen, they ask you to observe some kind of solid, all right, and they give you solid like this, like the one on the screen now. Wait, if you are given a solid that looks like this, you might think that it is white because it's so pale, all right, but it's actually pale pink. So the way that you can compare it is with paper. Paper is white, and then this one is not white. Sometimes you can't really see it that like this one. This one actually is not white, guys. This one is actually extremely pale pink. All right, you can only see it against paper. It's less white than a paper. Right? And what else? Oh, if you add just a few drops of manganate 7 to a bunch of ethanol, right? A lot of ethanol, then the manganate 7 will be reduced to manganese 2. You can't see pink because whatever manganese 2 in that solution, it's very dilute, right? So you can't see pink. You just see it as colorless. Yeah. So remember the context. Anything else?
Miss Lena, what do you mean when you said like density is the mass over volume and it's the same as mole over volume?
It's not the same, but it's equivalent to mole over volume, because if you increase the mole, you increase the mass, right? So it's equivalent to being to mole over volume. It's just different um, unit. That's all I can.
Oh, okay. Thank
Yeah.
you.
Thank you, Miss Lena.
Okay. Bye
Thank
bye.
you.
Bye.
Bye.